In this video, we will look at 2015 H2 Physics, Paper 2, Question 3. Let us first have an overview of the question. So this is a question on photoelectric effect, and we are given an experimental setup in Figure 3.1. This experimental setup is used to investigate the photoelectric effect. We are told that light shining on M has a single frequency and a constant intensity. The lower part of the circuit has a variable potential difference for us to change the potential difference across the two electrodes. Parts A and B are qualitative questions on which we are asked to state the condition for electrons to be emitted from the surface of M, explain why there is a minimum potential difference to reduce the current to zero, and explain why current does not continue to increase for positive values of V. Part C is a quantitative question to determine the frequency of the EM radiation, and Part D is a graphical question to sketch a new IV graph when the intensity is doubled. Let us start with Part A. In this part, you are asked to state the conditions for electrons to be emitted, and you need to do this in terms of energy changes. Let us first examine what happens when the photons hit the metal surface. The electrons are bounded to the metal. When a photon from the incident radiation hits the metal, it gets absorbed by an electron. The electron then uses some of this energy to break free from the metal, and the rest of it is manifested as the kinetic energy of the electron. The minimum amount of energy to liberate the electron corresponds to the work function of the metal, and these electrons that are least bounded leaves the metal with maximum kinetic energy. And the maximum kinetic energy is given by Ke max equals to Hf minus phi. Hence, the energy of the incident photon must be larger than the minimum energy to liberate the electron, that is the work function of the metal. This is the key condition for electrons to be emitted. However, before we move on to the next part of the question, we note that this does not seem sufficient for a 2-mark question. Hence, we will need to look for another point to include in the answer. The key concept tested here is Ke max equals to Hf minus phi. Hence, we will add that in for the 2nd mark. And we have the difference between the energy of the photon and the work function will be the maximum possible value of kinetic energy of the emitted electrons. This will be the 2nd point for the answer. Do use the number of marks as an indication of how much you should write. You should be able to allocate one key concept to 1 mark for your answer. Now we will move on to Part B. In Part B, we are given a graph of I versus V. And for Part 1, we are asked to explain why there is a minimum potential difference to reduce the current to zero. For this question, we will need to explain it in terms of the energy changes of the emitted electrons. To do this question, we first think about what happens when current is equals to zero. For current to be zero, there should be no emitted electrons reaching electrode C. To do that, we need to apply a negative potential difference with M at a higher potential than C, such that electrons will lose kinetic energy and gain in potential energy when it moves from M to C. The minimum potential difference will therefore correspond to the point when electrons with the most kinetic energies will have all their kinetic energy converted into electrical potential energy just before reaching electrode C. This will be the key point in our answer. Writing out the answer properly, we should have: number 1, for current to reduce to zero, none of the emitted electrons should reach C. Number 2, a negative potential difference is applied so that electrons will lose kinetic energy and gain in electrical potential energy as it moves from M to C. Number 3, there is a minimum potential difference Vs, as that is the potential difference which allows the electrons with the most kinetic energy to convert all their kinetic energy to electrical potential energy just before reaching electrode C. This should actually be the full answer. However, when we look back at the question, we note that this is actually only a 1-mark question. As this is a 1-mark question, the last point is therefore the most crucial point, and if I were to attempt the exam, this would be the point that I would be marking for. Next, we will move on to B part 2. For this question, we have to explain why the current does not increase for positive values of V. Hence, the region we are interested in is this region where the current saturates. Let us think of why current saturates first. We know that a current is registered based on the number of electrons collected per unit time at C. Current saturates when all the electrons emitted reach C. So what happens if we increase V after current saturates? Increasing V after the current saturates only causes the electrons to increase in kinetic energy upon reaching C. However, the number of electrons emitted per unit time from M does not change, and hence the number of electrons per unit time arriving at C also remains the same, and therefore the current will not change. Again, this is a 1-mark question, and hence the most important point to put in the answer will be the last point with the critical parts underlined. Now we'll move on to part C. In part C, you are given the work function of the metal M, and you are supposed to use figure 3.2 to calculate the frequency of the electromagnetic radiation. So, what are we given in figure 3.2 that's relevant? We are given an IV graph, and from there we see that we can actually get the stopping potential Vs. What is the relationship between the three quantities that allows us to find the frequency? We have Ke max equals to Hf minus phi, and we know that Ke max can be expressed as E times Vs. So using these two relationships, we can now solve for F, and from the graph, you can read off that Vs is equals to 2.2 volts. Substituting these and rearranging, we will have F equals to Vs plus phi over H. Putting in the values and converting into SI units, and we will be able to get the answer to be 9.65 times 10 to the power 14 Hertz. That is the answer. Finally, we move on to part D. In part D, you are told that light of the same frequency but double the intensity is shone onto the metal. You are asked to sketch the new IV graph for this new intensity. Let us think of what happens when intensity is doubled. When intensity is increased, the total number of photons per unit time is doubled as well. Suppose we associate each photon with a probability of emitting an electron. Then doubling the number of incident photons will cause the current to double. What about Vs, the other feature of the graph? The stopping potential is related to the maximum kinetic energy of the electrons. Since the frequency of light is unchanged and we're using the same metal and hence the work function remains the same, the stopping potential should remain unchanged. Those are the two key features we will need to put in the graph, and hence the graph should look like this. And with that, we have come to the end of the video solution for paper 2, question 3.